Okay, welcome back. So in the last video I explained to you about the latent heat and the latent heat of vaporization. Furthermore, I explained to you about the simple experiment that can be done using the concept of latent heat of vaporization. So in this video I'll be talking about the latent heat of fusion. So latent heat of fusion is very much similar to the latent heat of vaporization. So if you have watched that video, it will be very easy for you. And also latent heat of vaporization fusion is only different from the concept of latent heat of vaporization in that the change of phase is different. In the case of latent heat of vaporization, you knew that the phase change was from liquid to gas. However, in the case of latent heat of fusion, the phase change is from solid to liquid. So if you have not watched that video, and if some user here who is watching this video is not doesn't know about the concept of latent heat, let me introduce it first. So what is meant by latent heat? So I explained to you that in the last video, but I'll remind you again. So latent heat is the heat released or absorbed by a body or a thermodynamic system during a constant temperature process, right? So but okay, so now having explained about the latent heat of a substance, let me introduce what is meant by the latent heat of fusion. So I explained to you that in the concept of latent heat of vaporization. Now let's take the same approach in the case of latent heat of fusion. So what is meant by the latent heat of fusion? So latent heat of fusion is the specific latent heat L, right, of a substance is the quantity of heat which is required to change one unit mass of the substance from solid to liquid without any change of the temperature at the melting limit. So for example, if you take a sample of water, so at 0 degrees Celsius you can convert the sample of water from ice to water or from the solid to the liquid state. However, when you change water from between these two phases from solid to the liquid state, the temperature of water doesn't change, right? So the temperature doesn't change. So you can say, as I mentioned in the equation for the specific latent heat, that Q is equal to ml. So the unit of latent heat of fusion is joules per kilogram. So since you don't change the temperature here, right? Since you don't change temperature is not included in this equation. So as in the case of latent heat of vaporization, in the video that I described about the latent heat of vaporization, let me introduce a sample practical for the latent heat of fusion. To find the latent heat of fusion of ice, we use a sample experiment like this. We have two calorimeters, right? These are covered by heat insulating materials. So I'll explain as to why. And we have a stirrer, a lid, a thermometer, and water, right? So what we do here is that we introduce ice into the water and the calorimeter system, and we measure the temperature. So to do the experiment, we need some variables. So let's take the mass of the calorimeter and the stirrer to be m1, the mass of the calorimeters, the stirrer, and the water to be m2, the initial temperature of water to be θ1, the final temperature of water to be θ2, the mass of the calorimeter, stirrer, water, and ice to be m3. Also, let's assume that the specific heat capacity of the calorimeter is Z, that of the water to be Cw, and the specific latent heat of fusion of ice to be L. Now you know from the equation, or from the calorimetry equation, you can say that the the heat absorbed by one system is equal to the heat emitted by another. So you can say that the heat absorbed by ice and the heat absorbed by water after ice is melted is equal to heat emitted by the calorimeter and by water, right? So heat emitted by one system is equal to the heat absorbed or heat gained by another system. So the system that gains heat is the ice system, and the heat that emits now is the calorimeter and the water. Now this is completely in contrast to the situation that we faced when we were doing the practical on latent heat of vaporization. So therefore you can build up a relationship like this, and you can isolate L and from this equation we can find the specific latent heat of fusion of ice. So having introduced these variables, let's do the experiment. So as the first step of this experiment, what we do here is that we measure the mass of the calorimeter and of the stirrer, right? So then we can measure the mass, and then we boil water in the beaker until the temperature exceeds the room temperature by about 10 degrees of Celsius, and fill about 2/3 of the volume of the calorimeter with this water and measure the weight. So I'll explain as to why we did. So according to the equation, according to this equation, you can see here clearly that when the value of M3 changes by a very small degree, even a small degree can make the percentage error on L as high as possible. So the greatest care should be taken when measuring the mass of ice, right? So in this video I actually explained about the latent heat of fusion. In the last video I explained about the latent heat of vaporization. So these two videos combined finish the topic of practicals, physics practicals on latent heat. So in this video I explained to you about the latent heat of fusion, what is meant by latent heat, what is meant by latent heat of fusion, and I explained to you about a sample practical in which we could find the latent heat of ice, and explained to you some important points as well. So in the next video I will be explaining to you with a new concept on physics practicals, and thanks for watching this video, and see you then. So as the third step, what we do is that we record the temperature when the temperature of the system is about 5 Celsius above the room temperature, and I'll explain as to why we do such a step. So I explained to you about a simple and similar step in the case of the practical on the video of latent heat of vaporization. So if you have watched that video, you may be familiar with this concept that I'll be discussing with you, and I'll explain probably that on the important point section. So as a fourth step, what we do is that we add the ice cubes carefully to water. It's better if this is done while holding the ice cubes using a filter paper. So I'll explain as to why a filter paper is important. So it's recommended, it's not mandatory here. So the fifth step, what we do is we hold the ice cubes by the stirrer so that ice would not reach the surface of water. We just immerse these ice cubes, and we take the stirrer and we put the stirrer over the ice cubes, and we drown the stirrer along with the ice cubes, so that ice cubes are always below the surface of the stirrer, so that ice would not reach the surface, because you know that ice floats on water, so ice would not drown. So what we do is we take the stirrer and we together with the stirrer we drown, right? We immerse them to the bottom of the vessel so that they would not reach the water and the air surface. And so we repeat the procedures periodically by adding ice cubes until the temperature of the system is about 5 degrees Celsius, or 5 Kelvin less than the room temperature, and I'll explain as to why. And we record the final temperature of the system, and finally we measure the final mass of the system. So that's it about the experiment. Now let me explain you about some important points of this experiment. So I'll explain about those temperature variations in this part of the video. Alright, so the first important point when considering this experiment is that when the experiment is started at a temperature of 5 degrees of above room temperature and stopped when the temperature is 5 degrees Celsius below the room temperature, what actually happens is that now you know that after, now say you are now actually in a concept of like a number line. In a number line, so when you increase the temperature of a system, you lose heat, right? So when you increase the temperature, you lose heat, and also when you decrease the temperature, you gain heat. So what happens is that if you start the experiment at a temperature higher than the room temperature, there will be a heat loss on the system, and if you terminate or if you finish this experiment at a temperature of the same degree that you rose the temperature, same degree, now you rose the temperature by say about 5 degrees of Celsius, you will have to finish the temperature. You will have to finish this experiment by about 5 degrees of Celsius below room temperature. So the heat is gained when the temperature is increased by 5 or any degree of Celsius above the temperature you are considering of. And similarly, when it is decreased to a temperature, to the same degree below the room temperature, there will be a heat gain. So the total heat loss is approximately equal to the total heat gain. So the net heat change can be assumed 0 here. So now we know that in order to put this equation here, we considered that the heat loss to the environment as negligible. So in order to consider the heat loss to the environment as negligible, you have to consider that there's no heat loss, and also if there's a heat loss, you have to eliminate that with a heat gain of the same degree or an approximate degree. So what you do is a step like this: you increase the temperature and you simultaneously decrease the temperature at the end, so that you assume that the heat change is 0. So as I mentioned, filter paper is also necessary, but actually not mandatory. It's recommended if you can use a filter paper, because it can reduce the contact surface with ice. Now if you use your hand to do this, ice may melt on your hand and some water may actually be absorbed to your hand, right? Or if you do with another experiment. But in the case of a filter paper, the absorption is very low. So what happens is that you tend to reduce the contact surface, so that you tend to reduce the liquid part of ice. So when ice contacts with the physical surface, some amount of melted ice as water now may enter the calorimeter or into errors in calculations, right? So we reduce that error. It's recommended that you use a filter paper to touch the ice before releasing it to the water surface. And the third part is that, as I didn't explain this in the concept, actually in the method of this experiment, but it's also an important part. So the size of ice is also important. Now, as opposed to the concept that I explained to you in the case of latent heat of vaporization, in the case of latent heat of fusion, you need the size of the ice cubes to be of some size, right? Now in the case of latent heat of vaporization, what you did was you passed steam. You didn't have some physical shape or physical 3D shape, but in the case of this experiment, you need ice. So ice is a physical substance, not like steam. So you need to consider about the volume, the densities of no consideration. You need to consider about the volume. So what I mean is the volume by the size. So when the size of ice cubes are big, now we'll consider the ice cubes to be big, the medium and small, and consider as to what happens when we consider these size of different sizes, ice cubes of different sizes. So when the size of the ice cubes are big, the temperature of the ice will be less than 0 degrees of Celsius. So what actually means is that when you have large ice cubes, the temperature inside the ice cube may be somewhat different from the temperature on the outer surface. So there's actually a temperature gradient as opposed to medium and small ice particles. So when ice cubes are big, the ice gains heat to reach 0 degrees of Celsius due to this temperature gradient. However, this value will lead to errors in the calculation, as this step of heat gain is not included in the equation foil, because we did not include that foil, right? We just assume that the ice doesn't gain heat. Ice just converts to liquid water at the melting point, and we took the product of the mass of ice and the latent heat. So we did include the part in which the ice gain heat. So this will be an error in the calculation. So we have to omit big ice cubes. Also, the temperature is uncontrollable by using big ice cubes, because the temperature may exceed the dew point. So that's actually due to the temperature gradient I explained a little while ago. Now consider when the ice particles are very small, right? So we are going to the other extreme. Now we considered when the ice cubes are very big, so we are going to the other extreme in which ice particles are very small. When ice particles are very small, we can assume that the ice particles are almost like ice powder. So since ice powder cannot be obtained without some amount of water, using small ice cubes of ice powder is also erroneous, because we have not included the part where ice converts to water, in which ice has water at the beginning, right? Before converting to the liquid solid phase limit at 0 degrees Celsius at the melting point, we consider that ice melts into water, but we did not consider in the equation that ice has some water before melting, right? So that's actually erroneous. So we have to omit the consideration or the option of ice powder as well. So the best option would be to use medium size ice. So we'll not the effect of the presence of water in medium size ice will be also low, and also when using medium ice particles. So when using medium ice cubes, the temperature of ice is also controllable. There will be a minimum temperature gradient, and also the temperature will not exceed the dew point. So the best option is to use medium size ice cubes, and the temperature used for this experiment should be adjusted according to the dew point of the surrounding area, because as opposed to the concept of the latent heat of vaporization lab experiment I explained to you in the last video, we have to consider about the dew point in which it forms dew, right? So dew point is important when considering the temperature and the other factors that are necessary to find the value of L. And as I mentioned in the video, as the last important point of the latent heat of vaporization, in the case in the latent heat of fusion also, we have to measure the latent heat of since the latent heat of fusion is greater than the specific heat capacities of water and the calorimeter, greatest care should be taken when measuring the mass of ice. So the mass of ice is actually what I consider and what have to be the most precise measurement, because as I mentioned in the last video, according to this equation,